and share screen. And that's the wrong screen. Somebody, I think somebody just, this one. Someone has a question. Send me an email with your homework with a timestamp in the next 10 minutes, and I will take it. I'll make sure it gets into the system. Okay, Jordan? Just email it to me, and I will take care of it. If it's not late, I'm usually pretty good about taking it. If it is late, depends upon how late it is. There was no pre-lecture today. Homework 6 was due. We're going to do the exam review. Tomorrow, we're doing the remote exams by Zoom, by appointment only. If you have an appointment, I've sent you an email that says you're on the list. Or you emailed me and requested it. I might be on my list but not checked off. Exam 1, that looks horrible in this the blue background. Exam 1 will be in Frankie 436 on Wednesday at the regular class time. For everybody else, we'll start lab 4 this week, and lab 3 will be due on Friday. Lab 4 is a 4-week lab. It's on filters, not what the lab TA said on second order circuits. It is second order circuits, but they're filters. The first one's first order. What else is going on? There is a pre-lecture due, the class meeting after the exam. It's in P3. Okay. IEEE resume workshop tonight. The real career fair, I think they called it STEM session number 3, is on Thursday. Bring your resume. We'll throw darts at it. The whole idea behind these career fairs is usually the recruiter, whether it's in person or on Zoom, is going to spend about 10 seconds looking at your resume to decide if they want to talk to you more or they want to talk to the next guy. It may still be nice and talk to you for about 5 minutes. So the thing you want to see up at the top, what's your degree? Electrical engineering, that's a good thing. You're entirely hireable. The next thing is your skills. Skills you've learned in class, C programming, MATLAB, multi-sim, any kind of other tools you've used. Have you messed around with an Arduino, Arduino IDE, those kinds of things up at the top. Below that, projects, whether they're class projects, personal projects, or maybe projects you've done on an internship or at work somewhere. And then work experience if it pertains to EE. Don't go into a lot of details about jobs that are non-electrical engineering related, but if you kind of keep to that format, most people are going to at least talk to you long enough to figure out if they want to actually bring you in for a screening interview. Michael Greer. Nicholas Arnold by default. And we still haven't seen Ibrahim. Okay. So go to the career fair. They are hiring for internships. I just got a very frantic email from somebody who said, we've got this internship, we want a junior or senior though. And by junior or senior, they meant somebody who had taken 380. And we need to hire them within a week. And we forgot to put the rec in. So can you please just help me find somebody? And this used to happen to me right around career fair. It would happen, I get maybe 6, 7, 8 of these emails, and then maybe like once a week. I haven't gotten one of these for a year. So I think the job market's starting to open up when people are desperately looking for people. I could do the whole exam on this circuit, but I'm not going to. If you find you're struggling in this course, it's helpful that after this exam, it's a completely different course. It's a completely different textbook. We're going to start over with electronic circuits. So we're dealing with semiconductor-based devices. We're going to start with diodes, talk about semiconductor physics, and then MOSFETs. But if you feel like you're struggling, South Learning Center, which I think is called the Academic Success Center this year, has free tutoring resources available. They will schedule one-on-one, either Zoom or in-person meetings. Also, join IEEE. There's a bunch of people in there that have taken this class. A lot of people in there that know me. This is the first part, exam. Okay, so for the exam, you can bring 2 8.5 by 11 sheets of paper, anything you want written on it or printed on it, front and back, and you can use a calculator. I don't provide tables, and I don't provide stuff like that. So what do I write on the front page of this exam? Not much. There's name and your quest. Please fill in your quest. Don't ask me what it is. It's your goal, not mine. It's worth a point if you fill it in. And there's some circuits problems, yeah. There are 8 problems total. So this is a 75-minute exam. Your budget on that is probably a little less than 10 minutes a problem. Some of them are extremely short and you could answer them in 1 to 2 minutes. Some of them are going to take you longer. There's 6 points of extra credit. Your max score is 106 out of 100. That said, there's been people who've made 112 on one of my exams. There are stealth bonus point opportunities if you make me laugh. Grading exams is boring. If you can break it up, I appreciate it. There's always the +1. So your study priorities, these exam review slides and the solutions that go along with them, homework 1 through 6, for any problems anything you're having problems with, the audio review notes to go back and review concepts you don't quite remember, and the slides and the Nielsen reading books in the schedule. If you're really having trouble and you want to look at the book, at that point, I'd probably head for the IEEE room or one of the many discords, EE discords that we have going on now. Okay. First thing we looked at was first order circuits. There is one first order circuit on the exam. Calculating time. Oh, what do we have here? There's one of these and there's one of these. This is an easy problem. Don't miss that. This is the harder problem. When you calculate those time constants, the time constants RC or L over R, and the R is the REQ that inductor or capacitor sees at T equals 0 plus. So it's after you throw the switch. After you throw the switch. Okay. Throwing the switch problems, there were a lot of these on homework 2. Okay. Tim, send me an email. Wait, some people are taking the exam tomorrow. Let's see if I'll check tonight. I will write a note to myself and check. They're probably in the P2 section would be my guess. If they're not, I'll post them this evening. If I don't post them, then throttle me. Check for.
You're right, they are there.
Oh, thank goodness. Okay, good.
Thank you.
Okay, so we'll go through a throwing the switch problem. The other thing we looked at here, we looked at second order circuits. These were the long ones, the RLCs. We're going to go through one of those problems is dealt with in the slides. If you see anything on your exam that doesn't make any sense whatsoever, and it's labeled as extra credit, just put an answer down. If it makes me laugh, you probably get a bonus point. And if it's something really elaborate, sometimes you get a bonus point, but just don't leave it blank. These unit multipliers are used all over engineering, from Terra to Atto, and sometimes even EXA. Will we be given info regarding if the circuit has been sitting a long time? We just assume that it's been sitting a long time before the switch is thrown. I can't imagine me doing it otherwise. You can't solve the problems unless it's been sitting there for a long time. If you're not given initial conditions, you may have to derive the initial conditions. What did I do? Let me look at how the exam is worded, since it's right in front of me. Number 2, you're given the initial conditions. Number 3, you're asked to find the initial conditions. Number 4, you're given the initial conditions. So then you assume there's energy. Number 5, initial conditions don't matter. Same with 6, 7. On number 8, it says there's no energy stored in the system. So that means all the initial conditions are 0. So yeah, it states it one way or the other. Yeah. Yeah. If you don't know, assume that it's been sitting there for a long time. But if it's been sitting there a long time, there may still be initial conditions on the capacitor or inductor if there's an energy source at T equals 0 minus in the circuit. Okay, I think I covered all the parts of that. This is really important stuff that you need to keep in the back of your head for every exam you take from me in the future. Things that you know, and I start with the grad students like this a lot of times. They'll ask me a question and I'll write down on the board B equals IR. Let's start from there. Think about the basics and the fundamentals and what you can find easily. These are amazing equations too that I occasionally use. I occasionally use that one. Inductors didn't exist in my universe, but that's a whole other thing. V equals L di dt. We'll see inductors in here. KCL and KVL. I have had 380 students and I've given them, and this was like supposed to be the easy part of the problem, is I've given them stuff like this. This is going into a node. I have a circuit. There's 3 branches at here. This is 50 microamps. This is 25 microamps. And first part of the question is, what is the current here? And people can't answer it. So go back and think about those easy things first. The KCL, the currents going into the node equals the currents going out. If you can apply those to a simple circuit, you'll do fine. KVL when you have to. Most students don't like that so much. Capacitors are DC opens and inductors are DC shorts. So if it's before the switching event, you can assume it's been sitting there a long time. You can say those capacitors are DC opens and the inductors are DC shorts. When we deactivate sources, the voltage sources get shorted out. This is for like Thevenin equivalent, and there'll be more reasons to do this as we go along. And the current sources go to opens. And understanding voltage dividers and current dividers. There's not a lot of heavy duty 188 circuit analysis on this exam, but there's a lot of stuff, if you know and understand the basics, that you may have to apply. And that's true from now until the end of when you no longer see me anymore. For some of you, we'll get scared off and take 380 in the summer. But if you take 380 from me, you'll see this again. And if you take any of my senior electives, you'll see this stuff again. So time constants. I already told you the first problem is calculating a time constant. For an RC circuit, tau is RC. The default units are seconds or milliseconds or microseconds. We usually don't go into hours or anything like that. L over R will give you the same units. If there's more than one R in the circuit, you've got to find the REQ. And that's probably the easiest problem on the exam. Graphing. Yeah, okay. So this is back in the day before graphing calculators. We used to, and you can do this on your graphing calculator if you want to, and then put it on the page. But we want to draw a sketch of a graph. The first thing I would do is I'd figure out what V of 0 is. So V of 0, and looking at this right here, would be 7 minus 4, e to the 0th is 1, so it would be 3 volts. And V of infinity is 7 minus, this goes to 0, so it's just 7. So I could draw a really quick graph of this, t 0, and it goes out to infinity. V of 0 is at 3 volts. The final voltage is 7 volts. And we know it is exponential in between there. If you believe that looks like it's exponential. And the time it takes to get there is about 5 tau. And in this case, tau would be 1/3, so it would be 5/3 of a second. 1.67. And you haven't taken an exam from me before, so you don't know how much I hate fractions and answers like 3 pi. I usually don't take off, but I usually write a snarky note on there. Simply because when I'm going out in the lab and I want to measure this and check this against my theoretical prediction, my piece of test equipment is going to give me the answer in a decimal number. So it makes it easier for you to make a comparison as to how accurate your theoretical guesstimation was, and it was if something's going horribly wrong when you built it. Okay, so there's a problem sort of like this on the exam. It's different, but it's a sort of like this. We want to determine I of t. So we follow those steps. Remember, I of t, it just looks like this equation. There's 3 things I need to find. I need to find I of 0 plus, I of infinity, and tau. So first thing I want to do is draw the 0 minus circuit. Oh, that's just beautiful. T equals 0 minus. And it says it opens at t equals 0. It's closed for t less than 0. So it's closed. So I got a 24 volt source. I've got a 3 ohm resistor, a closed switch, a 4 ohm resistor, an inductor. It's been sitting there a long time. We just assume that. So it's a short, and it has some current going through it, and then an 8 ohm resistor. This is harder than the circuit analysis I ask you to do on the exam. Generally, for this one, I don't know the current coming out of this source. I could use a current divider on this back end, but I have to find this current first. And that current is going to be I source. Oh, I wish you'd taken 188 from me now. V source over REQ. So my REQ is 3 plus 4 parallel 8. And my VS is 24. And if I calculate that, I'm trying to go through these a little bit fast because I know I've got a whole bunch of stuff to do. That is 4.24 amps. And then we can use the current divider because now I know the current coming out of here is 4.24. This is I source, which means the current on the other side of the resistor is also going to be I source. I can use a current divider between the 4 and the 8 to get IL will equal 4.24 times the opposite resistor, which is 4 over the sum of the two that it's dividing between, 4 plus 8. And I can get IL is 1.41 amps. This is IL of 0 minus, which recall equals IL of 0 plus. So I've got one of these things. Then I draw, was I kind enough that I give you the steps? I'm reading the exam to you. I realize I'm doing this. Yeah, the steps on this problem are find the initial current, IL of 0 minus, find IL of 0 plus. After the switch is open, find the time constant for the inductor. Find the current through the inductor at t equals infinity. Find the current find the current I1 of t through the inductor. Okay. So literally, I'm stepping you through the steps of the problem in the different parts of the problem. So the next step is to draw the 0 plus circuit. Switch is open. It's a sudden event, so the inductor is inducting, and it looks like this. My tau is the equivalent resistance that that inductor sees. In this case, they're in series. If I'm an electron leaving that inductor, I have to go through both transistors. So my tau is going to be L over R, which is 4 over 12. It's a power circuit. It is about, what is that, a third of a second, 0.33 seconds. Okay, and then we need to find I of infinity. Well, even though this thing is initially charged to 1.41 amps, as time goes on, it's going to slowly discharge, so I of infinity is 0. We've got all the pieces. We plug it into the formula and we're done. Okay. Now the second part, I told you there is a first order problem, the complete thing. These second order problems are too long to put on an exam as one problem. Students mess up step 1, and then I have to go through and figure out if they did all the other steps right. So I don't do that. I break them up into smaller problems. There is one second order problem that does some of the pieces of that problem. Normally what we do is we go through, we determine if at t equals 0 plus, whether it's series or parallel. We calculate alpha and omega naught. We've determined which relationship I have here. Once we get that relationship, we know the form of the solution. It's either looks like this, and these could be either V's or I's or power or torque or speed or anything. It's just a differential equation. And I get the form of the solution here. I look at the form of the solution and I see, oh, this one needs S1 and S2, so I calculate S1 and S2. This one, I don't need any additional information at this point. And this one, I need to calculate omega D. So we calculate S1, S2, and omega D as needed. And we may have to solve for initial conditions. That is a separate problem. I give you a circuit. I give you the T equals, oh gosh, I give you the T equals 0 minus initial conditions, and I ask you what the 0 plus is on the circuit. Everybody's gonna miss that, I know. No, not everybody. Once I get the form of the solution, the thing I need to find is A1 and A2. I use this set of equations. Remember, since these are differential equations, all the V's could be replaced by I's if you're solving for a current. And I find the system of 2 equations and not 2 unknowns, and I solve it. And I told you this is too long. This is an initial condition problem. So being able to do all the steps yes, I do think I do hit all the steps of a second order on this exam. It's just over 2 problems. Here's a second order circuit. What we want to do here, let's just go through the process as a review. Switch moves from A to B at t equals 0. So at t equals 0 minus, it's in position A. We want to find V of t. Don't panic, follow the steps. It's like a 12-step program or something like that. Draw the circuits. There's wait till we get, oh, never mind. This is the longest math problem you'll ever see me do. So my 0 minus circuit, I've got a current source. I've got a resistor, it's 15 amps. I've got 4 ohms. I've got the 1 ohm isn't connected to anything, so it's dangling, so I'm just gonna leave it out. I've got an inductor that's been sitting there a long time. They're always been sitting there a long time at 0 minus. And I've got a capacitor that's been sitting there a long time. This is the kind of circuit analysis I expect you to be able to do. It's not hard, but there's still people who miss this. Okay. So basically, we've got IL that we need to solve for, and we've got VC. So my IL, the current from the inductor is going into an open circuit. So IL is 0. And that's 0 minus. The voltage across the capacitor, there's only one path for the current to flow. So the 15 amps has to go through that 4 ohm resistor and producing 60 volts across it. The capacitor is in parallel with the 4 ohm, so VC is 60 volts. And that's at 0 minus. Yeah, what we're looking for. We're asked to find the voltage across the capacitor. So looking ahead, I know to find the initial conditions for the voltage across the capacitor. From back here, doesn't matter what kind of damping I have, I'm going to need the voltage at 0 plus and the derivative of the voltage at 0 plus. So what the other thing I need is, okay, so that's the 0 minus circuit. That's as much as I can get from that. I'm going to keep this in my head though. So now we draw the 0 plus circuit. Now the switch has moved down here. The 4 ohm and the 15 amp have gone away. I've got a 1 ohm. It must be a power circuit, just say that. 0.25 henries. And I've got, oh, wait, sorry, forgot to draw the capacitor. I got 0.04 farads, AKA 40 millifarads. Okay. For this one, the things that we know at 0 plus is the current through the inductor can't change. So the current's still 0. And the capacitor voltage is still 60 volts, still going in the same direction. We can solve for all the voltages and currents in that circuit. Remember the thingy I did here, that this equals I equals C dV dt. We could solve for dV dt as just being I of 0 plus over C. So if we can get the current through the capacitor, we're done with this. Since it's a series circuit and they all share the same current, and this can't change instantaneously, IC is also 0. So my dVC dt at t equals 0 plus will be 0. Okay. We found the initial values and the derivatives of the initial values. Now we go to, that's me drawing the circuits and solving them, and I've already done that. The part I haven't done was part C. What are alpha and omega naught? Well, hopefully you have these on your note sheet. It's a series circuit, so alpha is R over 2L. If it was parallel, it'd be 1 over 2RC. Where am I at? R over 2L. Alpha equals R over 2L, and omega is 1 over root LC. So we plug in, which R do we plug in? We always look at the 0 plus circuit. And in that case, there's only one R. And we're going to be the REQ of that. So I go back and plug in the numbers. I find alpha's 2, omega naught's 10. Omega naught's bigger than alpha, so it's underdamped. And again, I can go back and look at that, look at those 4 key slides and get it in there. I've seen people copy the 4 key slides and put them on their note sheet and just make them small. Small enough that they can read them, well, big enough they can read them, small enough they can fit it all in there. This is the reason why I give you 2. I want you to keep them 2 for the final. Not necessarily for exam 2. Okay, so it's underdamped. I look up the form of the solution and it looks like this. The variable that I need, or the constant that I need in there, is omega D. So I'm going to have to calculate omega D. And omega D, omega naught squared minus alpha squared is, forget which order they come in, omega naught squared minus alpha squared. I've got alpha and omega naught. I can find omega D. Nothing really out of order or tricky like what we did in the lab. I know my V of 0 plus is A1, and I've already solved for that. It's 60 volts, and I know this equals 0. So A1 60, let me not get too ahead of myself. We calculated omega D, it was 9.79, and A1 is 60. This was 0, so 0 equals alpha times A1, which was 60, times omega D, 9.79, times A2. We can solve that for A2. So we've got A1 and A2, we've got omega D. We go back to the form of the solution and we plug in everything we know. On the exam. I just want you to learn this first, anything else. There is an initial condition problem on a second order circuit, and there is some pieces of this problem, like instead of going A through H, maybe I do A through E, or maybe I do D through H or whatever. It's a piece of this problem where I give you enough information at the start that you can finish it. Okay. And I did not put any of these singularity functions on the exam other than, I'll just be grateful for that, other than in Laplace transforms. You may have to take the Laplace transform of delta of t or u of t or something like that. Okay, because I know it's a lot of material for one exam. And now we're going to move on. Where are we at? PowerPoint, and I haven't crashed yet. Oh, and I am recording. I'm so proud of myself. Drawing Bode plots. I've already told you guys, there isn't a complex Bode plot on this exam. There's one where I just ask you to sketch it, and it either has, it has a K, and it either has a simple 0 or a simple pole associated.
I have a question.
Yes, thank you.
So when you're doing the when we're plotting the Bode plots,
Yeah.
where do we know where to start? Like when we do the final plot,
Yeah.
adding all the slopes together, do we start at K or do we start at the origin?
Do we start at K or do we? Okay, so generally when I'm drawing these graphs. Okay, so I've already told you what your graph looks like. It's a K and it's got a simple zero or a simple pole. So that K is going to look something like this. This is going to be KdV. Make sure you put it in dB. Now your simple zero or simple pole is going to be starting out at 0 dB and then at omega naught, whatever my omega naught is. Oh, no. Okay. Whatever my omega naught is, it's going to start to fall or go down. I'm going to try to finish this question without drawing a picture. So I kind of look at the values and I know 0 dB is going to be on the y-axis. I know K is going to be on the y-axis. And I know based upon if it's a zero or a pole that it can go up or down above that. So I just kind of ballpark it. And I usually put omega naught, whatever that is, since there's only one of them, somewhere in the middle of the x-axis. Is that what you were asking, or no? Some of it just takes time, and all I really asked you for was to draw a sketch.
Yeah, almost though. But so like I'm gonna annotate real quick. Like if this is like negative 20 decibels per second. All right, can you see that?
Can I see that?
I'm drawing.
Okay. It's not showing up on my screen. I can't see anything on my screen.
Oh, okay. All right. Never mind. But if it was like 20 decibels per second and then, I don't know, like 1K, do we start at 1K or do we start at the origin for the final?
There is no origin, because remember, this is a logarithm, so 0 is not an allowed value. So usually what I do is I put that omega frequency somewhere in the middle of the x-axis, and then I go back from that. So like 1 unit back from that would be 0.1 omega naught, and then 0.01 omega naught. If I go forward, it'd be 10 omega naught and 100 omega naught. And it's never actually going to reach 0.
I think what he means is like where on the decibels. Like,
Okay.
so like how you have the K, let's say K is 20 decibels, right?
Right.
And then you have a 0 at the origin. Like how do you adjust, or like how do you plot your first point? So like usually you start at 1, but like where at that time, like where on the decibel axis do you, where would your final plot start?
Where would your final plot start? You go back as far as you need to. I usually go back like about at least 2 orders of magnitude before omega naught and 2 orders of magnitude after.
No, so like in one of your videos, you had K and you had it might have been like a simple 0.
Right.
And your K was like -4. And like you added it at that point in time, you were like, oh, okay, so this is 29.
Okay.
This is -4, so you would start at 16 here.
Right. Oh, okay. So I was starting at each. It's just a matter. It's kind of a matter of experience, and I can kind of see.
And then like you did, like so you had.
Yeah.
Like omega.
I made those.
Omega equaled 1 and omega equaled 10. Like
right.
Through those points, you went just by that. Like
the slope, adding the slope.
And then after that, you were like, all right, from here, we're just gonna look at the slopes of each of those, and then
right.
See if they cancel or they add together.
And I made those 10 years ago. Yeah, there's nothing really complicated that is going to blow your mind on this exam with Bode plots. It is literally a K and either in a simple pole and a simple 0. So yeah, That is
All
it.
right.
I'm gonna reboot. I'll be back.